Hey everyone, welcome to the Joy of Coding at Portland State University. In this screencast, we'll learn about relational databases. Relational databases provide a robust and standard means for persisting the data that our applications rely on. Data persistence is a fundamental concept in contemporary software development, and while this content isn't meant to be exhaustive, PSU offers a couple of other courses in databases that will give you a much deeper understanding of the subject. It is meant to give you an overview of relational databases and how to work with them to author simple Java applications. So let's get started. So as I said, data persistence is a fundamental concept in software development. You write code, it deals with data, and you want to save that data for later. You want it to outlive the program that you're running. And what relational databases provide is scalable access to that data through standard programming interfaces. And it does it in a way that can scale and have it be highly structured so that many programs can access it at the same time and so that your data is well understood. Java has really good support for working with relational databases, and we'll learn about some of the APIs that Java provides for working with databases. But first, we're going to get some of the foundations of relational databases. We'll answer the question, what are relational databases all about? We'll also learn about SQL, the structured query language. And then we'll see how to use Java APIs to work with relational databases. It may go without saying, but data persistence is fundamental to software development. As we all learned in our introductory computer science classes, data that's stored in RAM is volatile. When the program goes away, when the program exits, that data is gone, it's lost. And so we probably learned how to persist data to files on the file system. The file system outlives the applications, the programs that run, but there's some limitations to working with a file system. If you're just using the plain old files that your operating system provides, you need to be very careful when it comes to having multiple programs accessing the same file at the same time, especially when two programs are trying to write to the same file. Another challenge that developers face when working with the file system is that it's hard to maintain data integrity. If you've got multiple programs writing to the same file, it's hard to keep them coordinated. And as your data grows, it becomes more difficult to search it efficiently. And finally, recall that while disk is cheap, it's not free. You must manage the disk usage. You just can't use disk forever. You'll eventually run out. So the bottom line here is that for a large-scale application, something that has lots and lots of clients, that has many concurrent processes and works with a huge amount of data, the file system alone is not sufficient. Now, a database, generally speaking, is a piece of software that manages data, and persistent data almost always. What this does is that it ensures that your data has integrity, that it has the state that you expect it to, and it also manages the underlying storage, how clients interact with it, things like that. It's very common to see databases deployed and managed completely separately from the applications that access them. And so a common architecture has the database server running in one application, as depicted on the right of the diagram here, and various client applications that connect to the database to work with it, to add data to the database, to fetch data from the database, to interact with it. Examples of those applications might be your website, your user interface for it, or perhaps a reporting application that runs on a separate server, maybe has some specialized reporting application for getting data out of the database and visualizing it in a way that makes sense to your users. An alternative architecture for using databases in an application is to embed the database inside the application, meaning that the database management software runs in the same process as the application itself. This is very useful when you have a self-contained application that needs a database to store its files, or for your automated tests that want to leverage the database. Now, there are many kinds of relational databases out there, but they have some similarities that I want to discuss now. All relational databases model data using tables. These are essentially something that looks like a spreadsheet. It's got rows and columns. Each row in the table represents an individual record of data. And each column in the table is an attribute of that data. Now, in relational databases, the columns have types, well-known data types. And we'll talk about those in a little bit. But here are some examples of tables that you might see in a relational database that manages a school course registration system. There might be a table called academic departments. And this table describes the departments at the university. every department has an ID in its ID column and its name. And so you see in this example, there are 3 rows, 3 records for the computer science, electrical engineering, and mathematics departments. In the academic departments table, the ID column is a number, an integral number, and then the name column is a string, it's text. Another example table is the courses table. This lists the courses that are offered at the university. The course table has 4 columns. Each course has an ID, it has a title, it has the number of credits, which is also a number, and then each course refers off to the ID of the department in which it's offered. So the first row, The Joy of Coding, is offered by the Computer Science Department, which has ID 267. Differential Calculus is also offered by Computer Science, and the Senior Seminar is in Mathematics. Now those IDs that are referenced across tables are referred to as keys. And keys are a fundamental concept in relational databases. They are the relation. They are the things that relate tables to each other in the relational database. There are 2 kinds of keys that I want to discuss. The first one is called a primary key, abbreviated as PK. And this is the value in one or more columns that uniquely identifies a row in the table. And this value must be non-null. You can't have a null primary key. It has to have a value, like those numbers in the tables we saw in the previous slide. Now, very often you'll want to have a primary key which is simple data, a number. You could use text data like a name, or some other piece of data which can change, something that's mutable, but that becomes problematic over time. For text columns, text tends to be larger than numbers. It's more expensive to compare them to make the reference between tables. And of course, if data is mutable, if it can change, then you not only need to change the primary key, but you need to change all the places that reference that primary key to make sure the data is consistent. So what you'll usually see in relational databases is that primary keys have a type called identity, which is a well-known type to the database, and the database knows to generate unique IDs for the rows in that table and assign each row its own identity. So the primary key identifies the row within the table. A foreign key is a reference from one table to another table's primary key. The database system itself enforces that the foreign key relationship is maintained, meaning that if you're going to create a database row that has a foreign key that references a primary key of some other table, the database won't let you insert that row unless the foreign key, the primary key in the other table, exists. Similarly, it won't allow you to delete a row whose primary key is used as a foreign key in a different table. And as I hope you can see, this keeps the data consistent. So for instance, the database would enforce that you can't delete a department as long as it has at least one course that references its ID. So when it comes to modeling data in databases, it helps to have a visualization of what data is there and how all the data relates to each other. So there's something called an entity relationship diagram, or an ERD, that has been used, and there are various flavors of these over the years. You'll see different kinds of notation. But the idea here is that you describe the tables in a relational database and how they're related to each other in boxes with arrows between them, right? It's the it's the standard way that we draw pictures in computer science. And so there are different kinds of relationships that tables may have. You can have a one-to-one table, which means that for every row in one table, there is another row in that table that corresponds to it. You can have a many-to-many relationship, which is, there can be many rows in one table that reference many rows in another table, or you can have a many-to-one relationship. It may not be standard, but I've found it to be helpful to annotate primary keys and foreign keys in your entity relationship diagram. And here's an ERD for the 2 tables that we discussed on the previous slides, the department slide and the course slide. As you can see, each table has an entry for the various columns that are in that table. So here again, we're describing the schema, not the data that is in the database necessarily. This is the shape of the data. And so a department, once again, has an ID, which is an identity. It is a primary key, it identifies it. And then it has a name, whose type is varchar, and we'll talk a little bit about what a varchar is, but basically it's a string, it's a bunch of text. That's what the name is. And then we see that the primary key of department is referenced by the department ID of the course. And a course consists of its own ID, the title of the course, and then the number of credits. And here we also annotate that the ID column of the course is the primary key, and the department ID is a foreign key off to the department table. And this notation comes in very handy for communicating about the structure of your database, and you can use it as a reference as you are writing code that accesses the database. Now, in addition to specifying the shape of the data, the schema of the data, and enforcing that schema in terms of what types can be inserted into the database and how the relationships are maintained, there are some key behavioral properties of relational databases that I want to be sure to call out. Now, as I said in the introduction, relational databases are designed to scale, to have lots of data, and to have lots of operations being performed against the database concurrently, all at the same time. So to make sure that the state of your database is what you expect, given all of this activity on it, there are these so-called ACID behaviors that relational databases implement. And ACID is an acronym for atomicity, consistency, isolation, and durability. So atomicity means that an operation is a single unit of work, and that it either happens or it doesn't. So an operation might have several steps. You might insert into these two tables, you might delete from that other table, you might update another table row. That operation that has multiple steps in it, atomicity guarantees that all those steps happen and are reflected in the database, or nothing happens at all. And of course, the canonical example of atomicity is transferring money from one bank account to another. It's in everybody's best interest to make sure that this operation always completes as expected. Another ACID property is consistency. Consistency means that the constraints on the database are always enforced. So for instance, you can configure your database to make sure that a bank account's balance can never be negative. And if someone attempts to set a negative balance to an account, the database will reject that. The third ACID property is isolation, which means that when an operation runs, it doesn't see the effects of another operation until that operation has completed, meaning that the view of the data is consistent for each operation. And finally, the D in ACID is durability, meaning that when an operation is successful, the effects that it has on the database, the changes that it made, are permanent. They don't go away. So even if there is a hardware failure or the database management system restarts, the results of successful operations last forever. And so relational databases provide these ACID properties of operations within something called a transaction. The idea here is that you're a client program to the database, and when you want to perform multiple operations, again, removing money from one bank account and putting it into another, you do this in the context of a transaction. And so you create a transaction, you do the work, and then you do something called committing the transaction. And we'll go into the details of that shortly. So as you can see, there are a number of pieces parts to relational databases. You have the shape of the data in the schema, you have the ability to interact with it. And relational databases support a standard language called SQL, the Structured Query Language. And the idea here is that this is a programming language of sorts that allows you to interact with the relational database in a standard way. That way, you as a developer only need to learn one programming language, and you can work with any database. Now, of course, there's an asterisk on this. Each database vendor may choose to provide additional language syntax or additional features, especially databases that have been around forever and predate the SQL standard. Certainly, for the scope of this course and what you'll be doing in it, stick to standard SQL. So, as I said, SQL is a programming language. It has a syntax, and that syntax has meaning. So it has syntactic and semantic rules. And I just want to note that here in the SQL examples that I provide, if there's a keyword in the language, meaning something that has a specific meaning, that will be in uppercase. That way, it'll just make it very clear what is a keyword in the language and then what is not. So, like, what's a table name versus an operation name. Unlike kind of the general purpose programming languages that you're probably used to, your Pythons or Cs or Java, SQL is declarative. You don't give it all the details about how to implement an operation. You just tell it what you want to be done. And then it's up to the database to implement that SQL and have it perform the operation that you expect. We'll be looking more at the language syntax here in a moment, but there are just a couple of things that I want to say here at the beginning. If you have multiple SQL statements, they are separated with a semicolon. And any text that follows two dashes is considered a comment. So you can have an SQL statement and then dash dash and a comment about it. Now, there are two categories of statements in SQL. There's something called DDL, which is the data definition language, and this is the syntax that works with the schema of the database, the shape of the database. It's the thing that creates tables, can add new columns, create something called indexes on them that are meant to improve performance. You use DDL when you initialize your application, when you initialize your database. It will create the tables. It will specify what the shape of the data is. The other category of SQL statements is called DML, the data manipulation language. And this is the set of statements that operate on the content in the database. So this is where you can add data to the database, or you can fetch data from the database. And you have the ability to refine the searches based on a number of different criteria. So as I noted before, the database columns have types associated with them. This is very convenient because it ensures that only correct data is added to the database. And so now I want to tell you about some of the standard data types that are supported in relational databases. There are several numeric types. So there's int and integer, which are 32-bit whole numbers, and there's also a 64-bit version of that called bigint. There's also a numeric type or decimal type, which gives you a decimal number, but it has a precision and a scale. So for instance, a decimal of 10,2 gives you 10 digits of precision and then 2 decimal places within that. And this is a very important data type because this is how you model money within a relational database. Because remember, money is not a floating point number. There's in US dollars, there's always up to 99 cents in any monetary value. You can't have 95.5 cents. However, if you have a different application that models data that is a true floating point number, you've got float and real for that. Databases can also store text data, various character types. So there is a car type, which is a fixed length string. So I say, oh yeah, car of 10 characters wide. It'll be padded with spaces. And so this is an interesting type. I consider this to be a legacy type, but it's a lot like learning C, right? Where you learn about C character arrays, and oh yeah, they have a fixed length, and then in this case of SQL, they are padded with spaces. More often, you'll see varchar column types, and again, this is a variable length string with a maximum length, and that's what the n is in the varchar n. And so if you go back and look on the previous slide, we talked about the name of a department being a varchar 255, which means that it is a string of up to most 255 characters. And then finally, there is a text or a blob type, which is a variable length piece of text with no character limit on it. And so this is where if you're storing a document or you're storing large amounts of text or small amounts of text, something that might vary a lot, you want to store that in a text column. SQL relational databases also have built-in support for dates and times. There's a date type, which is a year, month, and day. And there's also a time type, which is hours, minutes, and seconds. And I'm pretty sure most SQL databases will support milliseconds and probably even nanoseconds. And then if you want both a date and a time, you can use the timestamp type, which is also known as date time. And there are a couple of other noteworthy types in SQL databases. There's a Boolean, where you can have a value of true or false. And there's something called a blob, which is a binary large object, which is for byte data. So this is large pieces of binary data. Maybe they are binary documents, PDF files, or images, things like that, where again the database knows about this type and has certain optimizations for storing that data. And note that any of these types may have a null value, meaning that there's no value in it. And much like the Java programming language, null is a different concept than zero or an empty string. It means nothing's there as opposed to, well, zero's there. So I mentioned that DDL statements operate on the database schema itself, and here are some examples of how to do that. So the create table statement creates a table in the database. And when you create a table, you specify the name of the table as well as descriptions of the columns in that table. So here's an example of how the courses table might be created. So courses here again has 4 Columns, the first one is ID, which is an identity, and we notate that with a primary key. That's called a constraint on the column, so the primary key is the constraint. We do the same thing with the title of the course. Again, a varchar 255. It's not null, which means that you can't insert a null value into the course's table. Similarly, department ID, which is a foreign key off to the department's table, it's not null. Same thing with credits. And then after you've declared all of your columns, you can set up foreign key relations. And the way you do that is with the foreign key syntax, where you give it the name of the table column, which is a foreign key off to a column in another table. In this case, the department ID column in this table references the ID column of the department's table using that syntax. Note that when you use the not null constraint, you basically say that the value of the column is required, meaning that the client that inserts or updates data in the database must provide a value of that column. Now, there are some other DDL statements that I want to talk about here. You probably won't be using them in the course, but it's good to know. After your database table is created, you may need to change something about it. Add a new column, change the type of a column, change the name of a column, as your application and as the clients of the database evolve and change. And you do this using the alter table statement. Sometimes you find you might not need a table after all. Maybe it's the data is no longer used, or you're done with the database and you want to start over again. Here's where you would use the drop table statement from SQL. There's another DDL which is similar to drop table. It's called truncate table. And what that does is it removes all of the rows in a table, but it'll leave the table structure there in place. So this basically clears it out. Again, useful in test environments or if you ever need to clean up your production database. Now note that DDL statements, when you execute them, they happen immediately. Now we'll talk about transactions here in a little bit, but they're not subject to transaction boundaries like DML statements are. Okay, and speaking of those DML statements, we're going to talk about how you work with data in the database, not just the structure of the database. SQL is big on acronyms, and another acronym that you'll probably hear a lot about is CRUD operations. CRUD represents the 4 types of operations that can happen on a table. The SQL names for those operations are insert, and so that creates a row in the table, select reads a row, update updates a row, and delete deletes a row. So the SQL keywords are insert, select, update, and delete, and this gives you your CRUD operations. Now, you need to tell the CRUD operation what data you want it to work on. In addition to having your insert or your select, you also need to tell it what tables are involved, and this is the from portion or from clause of the CRUD statement. You can also have a filter on the data, which will tell which conditions apply to the data that you're looking for. So maybe you are doing a select, and you want to say, well, I only want to read the rows that have been updated in the last 24 hours. Something like that. And there's another optional clause that applies to select statements, which specifies the order in which the results are returned. That's an order by. And so there maybe we could order alphabetically by name or by enrollment date, those kinds of things. And we'll see some examples here shortly, but I hope what you're taking away is an appreciation for the breadth and the power of SQL, allowing you to do a lot of things with your databases. So let's take a look at the insert statement in SQL. Again, this is what's used to create a new row in the table. And the syntax for an insert statement looks like this. You have some keywords like insert into, and then you have the name of the database. And you specify the columns that will be impacted by this insert statement. So here we're going to insert the required columns, so title, department ID, and credits. And then we specify what values we're going to insert into the table. And the values correspond to each of the columns that you'll insert into. So the title will be The Joy of Coding, the department ID will be 267, and the credits will be 4. So as you may recall, the courses table has an ID column. We didn't explicitly set the value here because the database will create the value for the ID column for this row. And that's because the ID column is of type identity. So identity is a signal to the database that the database is the one that manages the value of that column, not the client. There's also the select statement in SQL. And what a select does is it queries the database, right? It goes looking for data in the database that matches some criteria. So here's an example of a select statement that will find information about the course whose title is The Joy of Coding. So the way you do that is that you say select a bunch of column names, so select the columns that you're interested in from a database table where, and this is your criteria, right? So here's where you can say, hey, I want all the courses whose title is The Joy of Coding. Now, select statements can be very complex. One of probably the first step that you'll take is doing what's called a join, which means that you want to query data from multiple tables. This is where we leverage primary keys and foreign keys. Here, we want to get information about the courses that are available at the university, and I want to include the name of the department in that query result. Now, the name of the department isn't stored in the courses table. It's stored in the departments table. And so what you do is you use a join operation to get information from both tables. So we'll say select c.title, d.name, and c.credits. And C and D are aliases for the courses table and the departments table. And you specify that in the from and the join clauses. So you say select c.title, d.name, and c.credits from courses, or table name, C, that's the alias for the table, sort of the variable, the easy name for the table. And then we'll join with the departments table, D, on c.department underbar ID equals d.id, meaning that we'll say, hey, listen, please put the query together and match up the row in the departments table that corresponds to the department ID in the courses table. Again, this is where those foreign keys come in really handy. This is how you can join tables together. And the database is optimized for doing these kinds of queries. So again, foreign keys are very helpful in the database. There's also the update and delete statements. The syntactically, they look a lot like insert and select. Hey, let's say that we want to set all courses that contain the word seminar to be 2 credits. And so we can do that by saying update the courses table, and set is the value that we want to set. So the credits column, give it the value of 2, and then where the title of that row is like, so it sort of matches a regular expression type thing. So the percent here is, hey, it's got some text before it, it's got some text after it, it may have some text before or after it, and it's got the word seminar somewhere in the title of the course. If you want to update a single row and ensure that only the single row is updated, because that first query, it'll update all courses. If you just want to update a single row, refer to its primary key in the where clause. So here, if we want to update the number of credits just for course 289, we would say the following. We'd say update the courses table and set the value of the credits column to 2 wherever the ID equals 289. The delete statement removes rows from a table. And so here we want to remove all of the courses that have been offered in BlackBerry app development. And here's how you express that. Right? You would say delete from the courses table where the title of the particular row has the value of BlackBerry app development. And recall again that the database will enforce those foreign key constraints. So if you attempt to delete a row that references, that who has a primary key that's referenced by a foreign key, the database will prevent that. The commit will fail. And speaking of commits, let's talk about database transactions. Now remember that database transactions are related to those ACID properties of the database. A transaction is the scope of work in which the ACID properties are enforced. So if you want to start a transaction, you use the command begin transaction, and that will instruct the database that that particular client is working within the scope of a transaction. As you can imagine, the database then has some bookkeeping to do in terms of what that transaction has done, what view of the data it has, things like that. But from a client point of view, you begin your transaction, you perform multiple CRUD operations within it. So maybe you're doing some selects and you're doing some inserts and some updates, those kinds of things. And then when you're done performing all those operations, you issue the commit command, which will request completion of the transaction. Maybe they'll perform all of the operations, but what it'll certainly do is then integrate those operations into the database, taking into account the work done by other transactions, potentially on that same data. Now, it might be the case that your client performs some operations and realizes that it doesn't want to do this work after all. Maybe it's detected some error or it wants to throw away the transaction. In that case, what the client will do is they'll issue the rollback command, and that tells the backend database to throw away that transaction, make sure that none of the side effects are viewable to other transactions, to other code, and then you go along your merry way. Now, note that transactions don't come for free. The database has to do some bookkeeping, as I said. There can be overhead here. Sometimes there can be a lot of overhead, comparatively speaking. So, when you work with transactions, you have to be cognizant of this. Often, you need a transaction to make sure that those asset properties are maintained. Again, it doesn't come for free. Now, you'll probably see this in the databases that you're using in this class, that the client will operate in auto commit mode, meaning that every DDL statement, every CRUD operation that you do is performed in its own transaction. Transactions are required when things get a little more complex, and so then out of the box, most clients just put you in easy mode, which means that every time you do a select, every time you do an update or a create, it occurs in its own transaction. So here's a more complex example of a database schema and querying it. It builds upon the department and the course that we already have. But this shows how you can then associate, you can make an offering of a course that is available for a certain academic term, the winter quarter or something like that. So you have your department and your course, just as before. Then you also have a table which is called academic term. And so this is the term that not only has a name, but also a start date and an end date. Note that both of those are dates. And then there's this table called course offering. And what course offering does is it relates a course to an academic term. Now, if you look at course and academic term, this is a many-to-many relationship, meaning that a particular course can be offered in many academic terms, and certainly an academic term can have many courses offered in it. And you want to understand for a particular course, and a particular term, what the relationship is between those. So, is a particular course offered in a particular term? And that's what the course offering table provides you. Here's where you use primary keys and foreign keys. So in the course offering table, yes, each offering itself has an ID, and really all that row is a course ID, which is a foreign key after the course table, and a term ID, which is a foreign key after the academic term table, put together. And given this schema, then you can author the query that I have here on the slide that will return all the courses that are offered in 2026. You want the names of all the courses, so and some other information. Here you do a select d.name, where if you read down a little bit, d is from the department table. And you have c.title and t.name. I had to make an alias for the department's name column called department underbar name, using the as clause right there, because both department and term have a column called name, so you need to disambiguate those. But anyway, we are selecting the name of the department, the title of the course, and the name of the term from now 3 tables, from the department table, the courses table, and the academic term table. Oh, I'm sorry, there are 4 tables in course offering, right. And then in the where statement, you need to glue all of this stuff together. So here we glue everything together by saying, hey, listen, we want to select that information where the ID of the department is the department of the course offering, and the ID of the course offering is the department of the course. And the term ID of the offering is the ID of a term. So basically, again, gluing everything together. And the start date of the term is after January 1st, and the end date is before December 31st in 2026. So this demonstrates the power of relational databases and really how you need to think about working with relational databases. You've got your data represented in these tables that have strongly typed columns, And then you can glue them all together inside of SQL queries, like this select statement that goes off and fetches the data that you need. And then you also need to tell it how that data is related to each other to make sure that you ultimately end up with the data that you want. So that's an overview of what SQL databases are all about. I did want to talk about some specific relational databases that are offered by various vendors. So these are things that you might have come across or that you might have heard of. So there are a couple of very popular commercial relational database vendors: Oracle and Microsoft SQL Server, IBM DB2. These are very popular, very robust, very expensive, because they power very important applications that run all sorts of systems all over the world. There are also some very good open source relational databases. So Postgres SQL is really meant to rival the commercial offerings of the first three by offering lots of scalability, very efficient access, but it's open source, and so this is very popular, especially in cloud-based applications. AWS and Azure make it very easy to provision and manage these databases. Another popular database is called MySQL or MySQL. Now, note, calling MySQL open source is a little controversial because MySQL was acquired by Oracle a while back. They wanted something that was cheap and easy to add to their product offering. So it's not exactly open source anymore, but it was for a very long time, and that made it really popular. And there was something called the LAMP stack, which was Linux. It's a Linux operating system, Apache, HTTP. M was the MySQL, and then P was either PHP or Python. But this was a tech stack that was very popular at one point because it was all open source and integrated with each other very well. So you might come across MySQL also. And then there's MariaDB, which is basically MySQL. Is from a lot of the same people, but it's meant to be a drop-in replacement. It works exactly the same. The configuration file format is the same, but it's open source, and it's true open source. It's not really owned by Oracle or anything like that. And so then MariaDB is also a very popular option for relational databases in open source environments. Now, all these databases are often run individually. You have a big database server and the appropriate, robust disks that back up all the data, that store all the data. And, this is what production applications need. But you may recall that we talked about embedded relational databases, and here are some that work really well for that. Probably the most popular one is SQLite. SQLite is implemented in native code. It's very efficient. It's meant for a very small memory and disk footprint. As a matter of fact, SQLite is available on every Android device. So, as we'll see later in the course when we talk about Android, SQLite is there. You've got a little database if you need one. Another embedded or embeddable database is H2. This is the database that we'll be using in this course. It's simple. It's a jar file. It's all embedded in Java, but it gives you a full relational database. You can perform all the operations you want. And most often it's used in an embedded situation, but it can also run standalone if that's something you really want. Another embedded relational database for the Java ecosystem is something called Apache Derby. This is kind of the predecessor of H2, and it was bundled with a JDK for many years. It was something that every Java deployment had. And again, the thinking at the time was like, great, this will be a nice embeddable database. And so if your Java application needs a small database, it's right there. They eventually realized that just made the JDK even bigger. It wasn't something that a lot of applications were leveraging, so eventually they took it out. But it's something that you may encounter in your travels. Now, I would be remiss if I didn't mention other kinds of databases that aren't relational databases. There is a set of databases called NoSQL databases, and what this is kind of a reaction to SQL. Hey, SQL isn't perfect, puts a lot of constraints on your data. It can be slower than other kinds of operation, and is really optimized for, again, that well-structured data. If your data doesn't look like that, or if there's another kind of database that you want to try, these NoSQL databases do the job very well. There are a class of databases called document databases. MongoDB is a good example. And what they do is that they store unstructured or less structured data, like JSON, right? This can be really anything. The nice thing about these document databases is that the database schema doesn't need to be uniform. There is no schema, so you can really put any kind of data that you want in there. Although having it just be JSON data you can optimize it more easily. You can also query it because it has some structure, but I guess it's not strongly typed. And so then document databases are really good at that. Another very popular kind of database are key value stores. So a good example of this is Redis. And the idea here is that it's just a persistent hash table. So if you're just looking up the values of keys, don't use SQL for that. That's overkill. You won't need to use all language syntax. Something like Redis is much lighter weight and just optimized for this particular problem. And so if you've got persistent data that you cache and just look something up by a session ID, a unique ID, something like that, key value stores are great. If you've got a lot of network data, things that have complex relations, graph databases like Neo4j are a good solution for that. You have a social media site, and you've got friends of friends, and you've got all these connections, and you want to be able to traverse those graphs very quickly, find relations between various parts of the data graph. These databases are great for that. If you've got an application that inserts way more data than it queries, so things like sensor networks or logging aggregators, wide column stores like Apache Cassandra are built for that. They have lots of support for distributing data over many stores to be able to efficiently query across all of that underlying data so that you can support petabytes of data in your application. So that's it. That was the introduction to relational databases. I just wanted to highlight a couple of things here before we break. So relational databases, what they do is they persist tabular data. So this is data that comes in rectangles. You've got rows of data, and each cell is a value for a column that has a strong type. What makes the databases relational is that the tables relate to each other via keys. So there are primary keys that uniquely identify a row, and then there are foreign keys that reference a row in another table. The database schemas, the structure of the databases can get complex, and so entity relationship diagrams, ERDs, represent that very well and make a nice communication tool. And then when it comes to working with databases themselves, the ACID properties of transactions are important to keep in mind as you're doing more and more complex work with your database. And what ACID guarantees is that the operations that are performed on the database are robust, especially when you have multiple operations happening at the same time. We saw a bunch of syntax for SQL, which is the structured query language, which is the standard programming language for relational databases. And this is nice because it's standard. It's only one set of syntax that you all need to learn and that tools need to support. And finally, we also learned about the so-called CRUD operations, which manipulate data in the database. So again, this is inserting new data. This is retrieving data from it, updating and deleting various rows and various pieces of data in the database. And so this is a good stopping point. We've covered the foundations of working with relational databases here. And in our next screencast, we'll explore how Java programs can work with relational databases. So thanks for joining us as a part of the Joy of Coding at Portland State University.